Hello friends, my name is Swanand. You are welcome at my channel at Info Rocket. Today we are going to discuss about ACE satellite. Advanced Composition Explorer ACE or Explorer 71 is a NASA's Explorer program satellite and space exploration mission to study matter comprising energetic particles from the solar wind, the implanetary medium and other sources. Real-time data from ACE are used by National Oceanic and Atmospheric Administration NOAA Space Weather Prediction Center SWPC to improve forecast and warning of solar storm. The ACE robotic spacecraft was launched 25 August 1997 and entered a Lysageous orbit close to L1 Lagrange point, which lies between the Sun and the Earth at a distance of some 1,500,000 kilometers from the latter. On 12 December 1997, the spacecraft is currently operating at that orbit. Because ACE is non-Keplerian orbit and has regular station keeping maneuvers or orbital parameters in adjacent information box are only approximate. As of April 2022, the spacecraft is still in generally good condition and is projected to have enough propellant to maintain its orbit till 2024. NASA Goddard Space Flight Center managed and developed an integration of ACE spacecraft. History. Advanced Composition Explorer ACE was posted in 1986 as a part of Explorer Concept Study Program. ACE is elemental and isotopic composition of accelerated newly from H hydrogen to Zn zinc, spanning 6 decades in energy per nucleon from the solar wind to galactic cosmic ray energies with the sensitive and with the charge and mass resolution much better than therefore possible. Following a phase A definition study, ACE was selected for development in 1989 and began construction in 1994. On 25 August 1997, ACE was successfully launched from Cape Canaveral Air Force Station by Delta II launch vehicle. The August 1997 launch was originally scheduled back in 1993. ACE observation allowed the investigation of wide range of fundamental problems in the following 4 major areas: elemental and isotopic composition of matter. A major objective is accurate and comprehensive determination of the elemental and isotopic composition of the various samples of source material from which nuclei are accelerated. These observations have been used to generate a set of solar isotopic abundance based on direct sampling of solar material, determine the coronal elemental isotopic composition with generally improved accuracy, establish the pattern of isotopic difference between galactic cosmic ray and solar system matter, Measure the elemental and isotopic evidence of interstellar and interplanetary pickup icons. Determine the isotopic composition of anomalous cosmic ray components, which are represents of a sample of local interstellar medium. Origin of the element and subsequent elementary processing. Isotopic anomalies in the meteorites indicate that the solar system was not homogeneous when formed. Similarly, the galaxy is neither uniform in space nor constant in time due to continuous stellar nucleosynthesis. ACE measurements have been used to search for difference between isotopic composition of solar and meteoric material, determine the contribution of solar wind and solar energetic particles to lunar and meteoritic material, and planetary to atmosphere and magnetosphere. Determine the dominant nucleosynthesis process that contribute to cosmic ray source material. Determine whether cosmic rays are a sample of freshly synthesized material. Example, from supernova or of the contemporary interstellar medium. Search for isotopic patterns in solar and galactic materials as a test of galactic evolution model. Forming the solar corona and acceleration of solar wind. Solar energetic particles. Solar wind and spectroscopic observation shows that elemental composition of solar corona is differentiated from that of photosphere all through the process which this occurs and by which the solar wind is subsequently accelerated are poorly understood. The detailed composition and charge state data provided by ACE are used to isolate the dominant coronal formation processes by comparing a broad range of coronal and photospheric evidence. Study plasma condition at source of solar wind and solar energetic particles by measuring and comparing the charge state of these two pollution. Study solar wind acceleration processes of any charge or mass dependent fractionation in various types of solar wind flow. Particle acceleration and transport in nature. Particle acceleration in ubiquitous in nature, and understanding its nature is one of the fundamental problems of space plasma astrophysics. The unique data set obtained by ACE measurement have been used to make direct measurement or charge and or mass dependent fractionation during solar energetic particles and implementary acceleration event. Constrained solar flare, coronal shock and interplanetary shock acceleration model with charge, mass and spectral data spanning up to 5 decades in energy. Test theoretical model of He-rich solar flares and solar Y-rays events. Instrumentation: Cosmic ray isotope spectrometer CRIS. The cosmic ray isotope spectrometer covers the highest degree of advanced compression explorer. Energy intervals from 50 to 500 MeV nucleon with an isotopic resolution of for element from Z2 to 30. The nuclei detected in this energy intervals are predominantly cosmic ray originating in our galaxy. This sample of galactic matter investigate the nucleosynthesis of parent material as well as fractionation, acceleration and transport process that these particles undergo in the galaxy and in interplanetary medium. Charge and mass identification with CRIS based on multi-measurement of dE and dx and total energy in stacks of silicon detector and trajectory measurements in a scintillating optical fiber trajectory SOFT hydroscope. The instrument has a geometrical factor of 250 cm. SR for isotope measurements. Electron, proton and alpha particle monitor EPAM. The electron, proton and alpha monitor instrument on a spacecraft is designed to measure a broad range of energetic particles over nearly the full unit sphere at the high time resolution. Such measurement of icon and electron in the range of few ten of keys to several MeV are essential to understand the dynamics of solar flares. Co-rotating interaction region CIRS, interplanetary shocks, acceleration and upstream terrestrial events. Large dynamic range of EPAM extends above 50 keV to 5 MeV for icon and 40 keV and about 350 keV for electrons. To complement its electron and ion measurements, EPAM is also equipped with a composition aperture CA, usually ambiguously identify ion species reported as species group rate at or individual pulse height event. The instrument achieves its large spectral coverage through 5 telescopes originated at various angles to the spacecraft spin axis. The low energy particle measurement obtained as same as time resolution between 1.5 and 24 seconds, and the ability of instrument to observe particle anisotropies in three-dimensional make EPAM an excellent resource to provide the interplanetary context for studies using the other instrument on the A spacecraft. Magnetometer (MAG). The magnetic field experiment on ACE provide continuous measurement of local magnetic field in interplanetary media. These measurements are essential in interpretation in simulation ACE observation of energetic and thermal particle distribution. The experiment consists of a pair of twin boom mounted triaxially flux gate sensors which are located 165 inches or 149 centimeters from the center of the spacecraft and on opposing solar panels. The two triaxial sensors provide a balanced, fully redundant vector instrument and permit some enhanced assessment of spacecraft's magnetic field. Real-time solar wind (RTSW). Real-time solar wind (RTSW) system is continuously monitoring the solar wind and producing warnings or impending major geomagnetic activity up to 1 hour in advance. Warning and alerts issued on NOAA allow those with system sensitive to such activities to take preventive action. The RTSW system gathers solar wind and energetic particle data at high time resolution for 4As. Instrument MAG, SWE, PAM, EPAM and SIS packs the data into low-rate bit stream and broadcasts the data continuously. NASA sends real-time data to NOAA each day when downloading science data, which combinates of dedicated ground station CRL in Japan and RAL in Great Britain, and time on existing ground tracking network and NASA DSN and USAF AFSCN. The RTSW system can receive data 24 hours per day throughout the year. The raw data are immediately sent from ground station to Space Weather Prediction Center in Boulder, Colorado, processed and then delivered to its Space Weather Operations Center where they are used in daily operation. The data are also delivered to CRL Region Warning Center at Hiraiso Station, Japan, to USAF 55th Space Squadron and placed on the World Wide Web. The data are downloaded, processed and dispersed within 5 minutes from the time and they leave ACE. The RTSW system also uses low energetic particles to warn approaching interplanetary shock and to get monitored the flux of high energy particles that can produce radiation damage in satellite system. Solar Energetic Particle Ionic Charge Analyzer SEPICA. The Solar Energetic Particles Ionic Charge Analyzer SEPICA was the instrument on Advanced Composition Explorer ACE that determined ionic charge states of solar, wind, solar and interplanetary energetic particles in the energy range from 0.2 MeV nuclei 1 to 5 MeV charge 1. The charge state of energetic icon contains key information to enable source temperature, acceleration, fractionation and transport processes for these particle populations. SPICA had ability to resolve individual charge states with substantially larger geothermic factor than its predecessor ULEIS on ISEE1 and ISEE3 on SEPICA was based to achieve these two requirements at the same time. SPICA was composed of high charge resolution sensor section and low charges resolution but large geometric factor sections. As 2008 instrument is no longer functioning due to failed gas valve. Solar Isotope Spectrometer SIS. The Solar Isotope Spectrometer SIS provides high resolution measurement of the isotopic composition of energetic nuclei from He to Zn. Z is equal to 230 over energy range from 10 to 100 MeV nucleon. During large solar event, ISS measure the isotopic abundance of solar energy particles to determine directly composition of solar corona and to study particle acceleration process during solar quiet time. SIS measures the isotopes of low energy cosmic ray from galaxy and isotopes of anomalous cosmic ray components which originate near by state detectors that provide measurement of nuclear charge mass and kinetic energy of incident nuclei. Within each telescope, particle trajectories are measured with a pair of two-dimensional silicon strip detectors instrument which custom very large scale integrates VLSI electronic to provide both position and energy loss measurements. ISI was specially designed to achieve excellent mass resolution under the extreme high flux condition encountered in large solar particle events. It provides a geometry factors of 40 cm, significantly greater than earlier solar particle isotope. Spectrometer. Solar wind, electron, proton and alpha monitor. The solar wind, electron, proton, alpha monitor experiment double or solar wind observation from advanced composition explorer. The observation provide the context of elemental and isotopic composition measurement made on ACE, as well as allowing the direct examination of numerous solar wind phenomena such as coronal mass ejection, interplanetary shocks, solar wind fine structure with advanced 3D plasma instrumentation, which also provide an ideal data set for both heliosphere and magnetosphere. Multi-spacecraft study, where they can be used in conjunction with other simultaneous observation from spacecraft as ULEIS. The SWEPAM observation are made simultaneously with independent Electron and Icon instrument in the order to save cost of ACE project. SWEPAM E and SWEPAM I are both are recycled flight spare from the joint NASA and ESA ULEIS mission. Both instruments had selective replacement, modification and modernization requirement to meet the A mission and spacecraft requirement. Both incorporate electrostatic analyzer whose fan-shaped fields of view to sweep out all pertinent look direction and spacecraft spin. Solar wind icon composition spectrometer SWICS and solar wind ion mass spectrometer SWIMS. The solar wind ion mass ion composition spectrometer and solar wind ions mass spectrometer on ACE are instruments optimized for measurement of chemical and isotopic composition of solar and interstellar matter. SWICS determined uniquely the chemical and ionic charge composition of solar wind, the thermal and mean spread of all major solar winds icon from H through FE at all solar winds speed about 300 kilometers per second. Protons and 170 kilometers per second. The resolved H and He isotopes, both solar and interstellar sources. SWICS also measured distribution function of both interstellar cloud and dust pickup ions to energize 100 keV/E. SWIMS measures the chemical isotopic charge and states composition of solar wind for every element between He and Ni. Each of the two instruments are the time of flight mass spectrometers and use electrostatic analysis followed by the time of flight and required as an energy measurement. On 23 August 2011, SWICS time of flight electronic experience and age and radiation includes hardware anomaly increase the level of background in the composition to migrate the effects of background. The model for identifying ions in the data was adjusted to take advantage of only ion energy per charge as measured by electrostatic analyzer and ion energy as measured by solid state detector. This has allowed SWICS to continue the deliver as subset of data products that are provided to public prior to the hardware anomaly, including ion charge state ratios of oxygen, carbon dioxide, and measurement of solar wind ion. The measurement of proton density speeds and thermal speed by SWICS were not affected by this anomaly and continued to present day. Ultra low energy isotope spectrometer ULEIS. Ultra low energy isotope spectrometer on the A spacecraft and ultra high resolution mass spectrometer that measure particle composition and energy spectra of element He and I with energy from 45 keV nucleon to few MeV nucleon. ULEIS investigate particle accelerated in solar energetic particle event, interplanetary shocks, and at solar wind termination shock by determining energy spectra, mass composition, and temporal variation in conjunction with others is instrument. ULEIS greatly improves our knowledge of solar abundance as well as other reservoirs such as local interstellar medium. ULEIS combines the high sensitivity required to measure low particle fluxes along with capability to operate in the large solar particle or individual icon. ULEIS features a wide range of count rate for different ion and energies that allow accurate determination of particle fluxes and anisotropies over short few minute time scales. Science results. The spectra of particles observed by ACE. The figure 1 shows the particle fluence total flux over a given period of time of oxygen at ACE for long time period just after the solar minimum, the part of 11 years solar cycle when solar activity is lower. The lowest energy particles come from the slow and fast solar wind with speed of about 3 100 to about 800 km per second. Like the solar wind distribution of all ions that of oxygen or superthermal tail of higher energy particles, that is the frame of bulb solar and wind. The plasma has an energy distribution that approximately a thermal distribution has a notable excess above 5 keV as shown in figure 1. The ACE team has made contributions to understanding the origins of these trails and their role in injecting particles into additional acceleration process at energies higher than those solar wind particles. ACE observed particles from region known as corrotating interaction region CIRS. CIRS formed. The solar wind is not uniform due to solar rotation. High speed streams collide with produce slow solar wind, creating shock waves roughly 2.5 astronomical AU, the distance between Earth and Sun, forming CIRS particles accelerated by these shocks are commonly observed at 1 AU below energies of 10 MeV per electron. ACE measurement confirmed that CIRS include a significant fraction of singly charged helium formed when interstellar neutral helium is ionized. At yet higher energies, the major contribution to measured flux of particles due to solar energetic particles SEPS associated with interplanetary IP shocks when shocks driven by fast coronal mass ejection CMES and solar flare enriched evidence of helium-3 and helium ions showed that superthermal trails are the main seed of population of these SEPS IP shocks traveling at speeds up to 2000 km per second. Accelerate the particles from superthermal trails to 100 MeV per nucleon and more. IP shocks are particularly important because they can continue to accelerate particles as they pass over ACE and thus allow shock acceleration process to be studied in situ. Other high energy particles observed by ACE are anomalous cosmic ray ACRS and that originate with neutral interstellar atoms that are ionized in interheliosphère to make pickup. Ions are later accelerated to energy greater than 10 MeV per nucleon in the outer heliosphère. ACE also observes pickup ions directly. They are easily identified because they are signally charged. Finally, the highest energy particles observed by ACE are galactic cosmic ray GCRS through the accelerated shock waves of supernova explosion in our galaxy. Other findings from ACE: shortly after launch, SEP sensors on ACE detected solar events that had unexpected characteristics like most large shock accelerated SEP event. These were highly enriched in iron and helium-3 as are much smaller flare-associated impulsive SEP event within the first year operation is found many of these hybrid events, which led to substantial discussion within the community as to that condition could generate them. One remarkable recent discovery in heliospheric physics has been ubiquitous presence of superthermal particles with common spectral shape. This unexpectedly occurs in quiet solar wind in disturbed conditions downstream from shocks, including CRIS and elsewhere in heliosphere. These observations had led risk on Galoreker to suggest a novel mechanism for particle acceleration. Another discovery has been that the current solar cycle has measured the sunspot CME and SEP have been much less magnetically active than previous cycle MC, ETAL have shown that the dynamic pressure of solar wind measured by ULEIS satellite over all latitude and by is elliptic and elliptic plane are correlated with declining in the same time for about 2 decades. They conclude the sun that had been undergoing a global change that affected overall heliosphere simultaneously. GCRS sensitiveness were increasing and in 2009 were highest record during the past 50 years. GCRS have most difficulty reaching Earth when the sun is more magnetically active, so the high GCR intensity in 2009 is consistent with a globally reduced dynamic pressure of solar wind. ACE also measure evidence of cosmic ray nickel 59 and cobalt 59 isotopes. These measurement indicates that a longer than half-life of nickel 59 with bound electron 7.6 by 10 years elapsed between the time nickel 59 was created in a supernova explosion and the time cosmic rays were accelerated. Such long delay indicates that cosmic rays come from acceleration of old stellar or interstellar material rather than from fresh supernova ejecta. ACE also measure an iron 58, iron 56 ratio that enriched over same ratio in solar system material. These and other findings have led to theory of material. And other findings had the origin of cosmic ray in galactic superbubbles formed in regions where many supernova explode within few million years. Recent observation of Proton of freshly accelerated cosmic ray in the Sagittarius superbubble by the Fermi Gamma Ray Observatory support this theory. This is a satellite. This is rocket in which a satellite was launched. This is oxygen fluence recorded by a satellite. So that's it for this video. If you like this video, then click on like button, and if you are new at my channel, click on subscribe button. And if you want more interesting video about rockets and satellites, then select bell icon to all. Thank you.